So case 1, let us consider estimation of sigma to power r, where r is different from 0. So you have to first guess what should be the induced group of transformations on the Xn space. So note that my Xn space is nothing but, because sigma is positive, so sigma to power r would also be positive, and sigma can take value, any value between 0 to infinity. So sigma to power r can also take any value between 0 to infinity. So I take my Xn space to be 0 to infinity. All right. Now once I have identified my Xn space, I have to see what should be the induced group of transformations on the Xn space. Original problem, I am interested in estimating sigma to power r. In the transform problem, sigma gets transformed to b sigma. So sigma to power r gets transformed to b sigma to power r, which is nothing but b to power r, sigma to power r. Sigma to power r was anyway estimated in the original problem. So my group of transformation on the Xn space is nothing but b to power r times a. So let g tilde is nothing but g tilde of bc, such that b is positive, c is enough. And what is my g tilde bc? A, that is nothing but b to power r into a. A belongs to Xn space, b is positive. Now I have to choose a loss function which is invariant. So loss function L theta A is invariant if and only if what happens? L of g bar b c theta A, sorry, g b c tilde A so loss in the transform problem is same as loss in the original problem. So unit of measurements do not affect the loss function. For every theta belongs to r cross 0 to infinity, which is your parametric space, and a greater than 0. So what does that mean? L of g bar b c theta is nothing but mu gets transformed to b mu plus c. Sigma gets transformed to b sigma. What is a g b tilde c? This is b to power r a. This is what I saw just now. This would be same as L of mu sigma a for every theta in r cross 0 to infinity and a positive. So there are 2 degrees of freedom over here, because I can choose my b, I can choose my c. So one immediate thing I get is if I get b as 1 by sigma, this gets simplified, it becomes only 1. So once I have chosen b to be 1 by sigma, I can choose c to be minus mu by sigma. So this implies that L theta A is nothing but L of, so I have chosen b to be 1 by sigma, so and c to be minus mu by sigma, so that becomes L of 0, comma 1, and b as so a by sigma to power r. So which is same as some function of only a by sigma to power r. Now converse is always hold. Any loss function of above type is invariant. Why? Because if it is of this type, let us try to see what is L of B mu plus C and B sigma. So here only B sigma is coming. So it would be A to power R, B to power R, A, and then that would cancel. So it's just straightforward to see. Right? Because what you can say is, if you have to say it, what you have to see is L of G bar BC theta G tilde BC A. What is nothing but? And LGBC theta, what happens? Mu gets transformed to B mu plus C. There is no mu over here. Only sigma is there. So sigma gets transformed to B sigma. And what happens over here? Under G tilde, A transformed to B to power R into A. So it is W B to power R A. And sigma under G bar BC theta gets transformed to B sigma to power R. So B to power R, B to power R gets cancelled, which is nothing but W of A by sigma to power R, which is nothing but L theta A. So the converse is also always true. So what it suggests is my loss function would be invariant if and only if it is a function of A upon sigma to power R. So I'll take my loss function to be of this type. So what I assume is that L theta A is W of A by sigma to power R. Theta belongs to capital theta. A belongs to A. And what I assume is my W is convex in A. What I also assume is this is convex, so that I can restrict myself to only non-randomized invariant decision rules. So let this convexity helps us in reducing the class of estimators under consideration. So that means I need not consider randomized estimators. So let us DI to the class of non-randomized invariant estimators. So it's very algorithmic. You might have seen that exactly the same things we did while dealing with location families. We repeated the same arguments for the scale family of distributions. The only difference is the group of transformations under which the problem remains invariant. That changes. In the location case, it was a additive group of transformations. In the scale case, it was a multiplicative group of transformations. Now, in the case of location scale family, it is a affine group of transformations. So accept that, otherwise everything is very structured. So let us see what is the definition of invariant estimator. So delta belongs to DI if and only if delta of G BC of X. So this is the observation in the transform. This would be same as you don't change the transform, you just change the action. So changing the action is taking G, applying G tilde BC, and delta of X remains the same for every X. B positive, C in R. So what does that say? This is equivalent to saying that delta of B of X1 plus C, B of Xn plus C is nothing but B to power R delta of X1, X2, Xn. For every X, for every B positive, and for every C belonging to R. So first thing it suggests is, what I do is, I take B to be 1. So this suggests that delta of X1 plus C, Xn plus C is nothing but delta of X1, X2, Xn. So I've got 1 degree of freedom over here for every x and c belonging to R. So what I do is I take c to be minus xn. So this implies that delta of x1, x2, xn is same as delta of x1 minus xn, xn minus 1 minus xn. So which is some function of x1 minus xn, x2 minus xn, and xn minus 1 minus xn. I can call them as d1, d2, dn minus 1. So let me call this as v of d1, d2, dn minus 1, 0. Where? So I'll have to define the corresponding random variables over here. I'm defining that by capital Di. This is nothing but xi minus xn. So what does this suggest? This suggests, part 1, that any invariant estimator, first of all, has to be a function of d1, d2, dn minus 1. So this suggests that delta belongs to di if and only if delta is a function of d1, d2, dn minus 1. So what I do now is I look at what is the PDF of d1, d2, dn minus 1. So joint PDF of d, which is d1, d2, dn minus 1 is, so what I have to make? I have to make a transformation xi as di, xn let me put as t. So first I try to find out the joint PDF of d1, d2, dn minus 1 and xn, and then I integrate out the unwanted variable xn. So xi is di plus ti is equal to 1 to n minus 1. And xn is nothing but t. So joint PDF of d1, d2, dn minus 1. First I'll write down the joint PDF of x1, x2, sorry, joint PDF of d1, d2, dn minus 1 and xn, right? And then I integrate out the xn variable, that means corresponding variable t over here. So what is the joint PDF of d1, d2, dn minus 1 and xn? So 1 by sigma to power n. Now Jacobian in this case would be 1 because it would be a diagonal matrix with 1 element everywhere. And last column would be 1, 1, 1, 1. So triangular matrix in fact. Upper triangular matrix, so determinant would be the product of diagonal elements. Each diagonal element is 1, 1, 1, 1, 1. So 1 by sigma to power n, f of x1 minus mu by sigma. So x1 minus mu is nothing but d1 plus t minus mu by sigma. xn minus 1 means dn minus 1 plus t minus mu by sigma. And xn, t minus mu by sigma. So this is a joint PDF of d1, d2, dn minus 1 and xn. But I have to get a joint PDF of d1, d2, dn minus 1. So I have to integrate out the unwanted variable, which is minus infinity to infinity of this into dt. So this is a joint PDF of d1, d2, dn minus 1. Okay, what I can do is I can make the transformation t minus mu by sigma as t prime. All right, t minus mu by sigma as t prime. So what do I get over here? So once I make this transformation, this 1 sigma will go into the Jacobian part. So this would be left with minus infinity to infinity 1 by sigma to power n minus 1 f of t minus, so d1 by sigma dn minus 1 by sigma d1 by sigma plus t everywhere would come, sorry. d1 by sigma plus t, dn minus 1 by sigma plus t, t. Now, this can be written as 1 by sigma to power n minus 1 g of d1 by sigma, because it depends on d1 only through d1 by sigma, dn minus 1 by sigma. So, very interesting thing. What you observe is any invariant estimator of sigma to power r is a function of d1, d2, dn minus 1, and d1, d2, dn minus 1 has this structure, which is same as a scale model. But we also know that delta belongs to di implies that, now here I have taken b to be 1, now I take c to be 0 and I keep b, implies that delta of bx1 bxn is same as b to power r delta of x1 x2 xn. But delta of bx1, we have seen that delta of x1 x2 xn is nothing but v of d1 d2 dn minus 1. So that means v of d1 is this component minus this. So that means b of d1, b of x1 minus xn, then b of dn minus 1. Actually, this whole itself, there is no need to write down this as 0, because this is a function of this. So I can write down this as v of d1, d2, dn minus 1. So v of b of d1, b of d2, b of dn minus 1 is same as b to power r v of d1, d2, dn minus 1. What does this say? My any estimator would be function of d1, d2, dn minus 1. That means it would be v of d1, d2, dn minus 1 for some function. And it says it should satisfy the property of a scale invariant estimator for the scale probability model, which we did before. Now, in this case, I have to now see whether my loss becomes invariant or not. So, L theta A is W of A by e to power r. So, my loss function is also of the same type, as similar to what we considered in the scale model. So, my invariant estimator has to be function of d1, d2, dn minus 1, and it should satisfy this property, which is the same as the one which we had in the case of a scale probability models. And now, in the case of scale probability models, I know what is the best invariant estimate. So, what you conclude first over here is delta belongs to di if and only if delta of is same as v of b d1 it is a function of d1, d2, dn minus 1 for some v which is from Rn minus 1 to R. In fact, we'll have it from 0 to infinity because my Xn space is 0 to infinity, such that what is the property V should satisfy? we have seen that V of B1, D1, B D2, B Dn minus 1 So in fact, my original problem has reduced to the scale probability model problem only, because it says I should only restrict to estimator, which are functions of d1, d2, dn minus 1, but d1, d2, dn minus 1 has a PDF which belongs to scale family. Invariance here applies because of this fact. So you can get the best invariant estimator. So let me write down the exact result if I have it with me over here. So what is the MRE? So in fact, if you want, in the location case, what we had seen, this says that V of d1, d2, dn minus 1 is nothing but, I have to replace it by, I can take B to be 1 upon mod of dn minus 1. So this means this is same as V of d1 upon dn minus 1. In fact, d1 upon mod of dn minus 1, dn minus 2 divided by mod of dn minus 1, and dn minus 1 by mod of dn minus 1. And we had seen that this is a one-to-one function of d1, d2, dn minus 1. So this is some function of d1 upon dn minus 1. All right. So what we have seen, delta belongs to di. What we have seen, V of d1, d2, dn minus 1. This would be 1 upon mod of dn minus 1 to power r also, right? I am taking B to be 1 upon mod dn minus 1. So this would be nothing but mod of dn minus 1 power r. So this is same as mod of dn minus 1 to power r. So delta belongs to di if and only if delta of x is nothing but mod of dn minus 1 to power r divided by, so v star I can take as 1 upon u of d1 upon dn minus 1. So you can write down this as d1 upon dn minus 1, dn minus 2 upon dn minus 1, and dn minus 1 upon mod of dn minus 1. And then, as usual, these are scale invariant estimators. So if you want, you can replace it by any scale invariant estimator. So this all is exactly on the same lines as we did in the scale family. So let delta naught belonging to di be fixed. So that means it is any scale invariant estimator which is of this type. That means it is a function of d1, d2, dn minus 1, and v of b d1, d2, dn minus 1 is same as b to power r, b d1, d2. Then any other estimator delta belongs to di if and only if delta x can be written as delta naught x upon u of d1 upon dn minus 1 dn minus 2 upon dn minus 1 and dn minus 1 upon mod of dn minus 1. So note that if my delta naught is also a function of d1, d2, dn minus 1. So let me call this as w1, w2, wn minus 2, wn minus 1. For given w, let u star, which of course depends on w, minimizes that conditional expectation, right? So, which was mu is equal to 0 and sigma is equal to 1, because here g bar again acts transitively of L of A, which is nothing but in fact delta naught is a function of d1, d2, dn minus 1 only upon u of so let me call this as u of w. So u, because conditional expectation I am talking about, so this u will not depend on w, I can make it this as given w. Then the MRI is delta star x, which is same as delta naught x by u star of w. Now, in the location and scale family, we saw that this was d and z, and they were turning out to be ancillary in the respective cases. So if here also my w turns out to be ancillary, then I can choose delta naught to be a function of a complete sufficient statistic wherever it is possible, and that will make my life simpler. That means I don't have to consider this conditional expectation. So let us try to see what is w. W is nothing but d1, which is x1 minus xn, divided by xn minus 1 minus xn. Then xn minus 2 minus xn divided by xn minus 1 minus xn. So this is d1 divided by dn minus 1, dn minus 2 divided by dn minus 1, and then dn minus 1 divided by modulus of so I have to see whether this is invariant or not, this is ancillary or not. So generally, to check whether a statistic is ancillary or not, you try to make certain transformation in the original distribution so that the transformed variable have a distribution which does not depend on the parameter. So original distribution was 1 upon sigma to power n f of x1 minus mu by sigma, xn minus mu by sigma. So that means this suggests that if I take Zi as xi minus mu by sigma, I is equal to 1 to n. Let me just make some margins over here. Then, if I take the vector z, z1, z2, zn has PDF, you can easily see. Everywhere you have to put xi minus mu by sigma as zi, and because of this zi sigma everywhere, 1 by sigma to power n would get consumed into the Jacobian part. So this has PDF f of z1, z2, zn. And this does not depend on any parameter. So what I do is now I try to write down this w in terms of zi's. And if I'm able to write down this explicitly in terms of zi's, then it is some function of z1, z2, zn. And since distribution of z1, z2, zn does not depend on theta, distribution of any function of z1, z2, zn will not depend on theta. So that is very simple. x1 would be nothing but sigma z1 plus mu. So sigma z1 plus mu. Sigma zn plus mu. So mu gets cancelled. So it would be sigma of z1 minus zn. Same thing over here. Mu would get cancelled. And it would be sigma of zn minus 1 minus zn. Sigma numerator and denominator will also get cancelled. So this would be nothing but z1 minus zn upon zn minus 1 minus zn. Zn minus 2 minus zn divided by zn minus 1 minus zn, and then zn minus 1 minus zn mod of zn minus 1 minus zn. But we have already seen that distribution of z1, z2, zn does not depend on theta. So distribution of any function of z1, z2, zn does not depend on theta. So this implies that this vector is ancillary. So if delta naught belonging to di is a function of complete sufficient statistic, then by Basu's theorem, this conditional expectation would be independent of w. So that means minimizing u will also not depend on what w was fixed at. So this would be u would be a constant. So then the MRI is delta star x, which is delta naught x by u star, where u star minimizes psi of u. E0, 1. E0 means mu is 0 and sigma is 1. And the reason for that is because here d bar again acts transitively on the parameter space, so risk of any invariant estimator would be constant. Delta naught x. Given here. All right. Now to see, you can directly see it acts transitively, g bar acts transitively on theta, or the way I did, I saw that when I'm applying invariance over here with a fine group of transformation, my problem reduces to estimating sigma to power r in the scale family of distributions. And then I applied the theory of scale family of distributions to get an estimator of this. Because the invariance principle, the moment I apply, I see that any invariant estimator of sigma to power r is a function of d1, d2, dn minus 1. So that means the whole inference depends on observations only through d1, d2, dn minus 1. And this d1, d2, dn minus 1 again had a PDF which belongs to scale family. All that invariance holds. So I can apply the theory of scale probability models over here, and that is what exactly I did over here. Okay, so now we saw that in the case of scale probability models, I'm able to get the best invariant estimator under squared error loss function. So that I can directly apply here. So what do I get over here? So under square error loss L theta A as A by sigma to power r minus 1 whole square. What is this minimizing delta star x? Would be nothing but 1 upon u star we had seen over there was nothing but expected value of mu is equal to 0, sigma is equal to 1 of delta naught x given w divided by E01 of delta naught x, delta naught square x given w, and then delta naught x. So this is what the MRE turns out to be. Note that here delta naught depends on x only through d1, d2, dn minus 1. And of course, if you choose delta naught to be a function of a complete sufficient statistic, then w being ancillary, this will turn out to be a constant. Okay, so in the case of squared error loss function, this also turns out to be one getting from the direct formula. And what was that? If you recall a scale family, it was 0 to infinity f of tx1, tx2, txn dt divided by so on, and t to power n plus b minus 1. So this is same as 0 to infinity